Hello, welcome to Fundamentals of Acoustics. Today is the last day of the second week of this course, and what we plan to do today is continue the discussion on Bode plots. Specifically, what we will do today is we will start by developing a Bode plot for magnitude for a simple 0. So, Bode plot for a simple 0. So, in this case the transfer function h of s is a simple 0, that is s plus z. Now, we know that when we construct Bode plots, they are in context when the complex frequency equals j omega. So, h of omega equals z plus j omega. So, in decibels I can express it as dB equals 20 log 10 z plus j omega. Now, this decibel value of the amplitude or the magnitude of h, what we will do is, again as I said, we have asymptotic representations of h. So, we will consider two scenarios. The first scenario is when omega approaches 0, then dB approaches 20 log of 10 z, and when omega approaches infinity, then the value of decibel approaches 20 log of omega. So, both of these are base 10 units. So, this will give me my low frequency asymptote, and the second relation will give me my high frequency asymptote. So, now I will plot the asymptotic response for a simple 0. So, I have on the x axis I plot log of omega to the base 10, and on the y axis I have my low frequency asymptote, which is this, and the low frequency asymptote is a straight line and its value is, so this is in decibels, its value is 20 log of 10 of z. And then the high frequency asymptote we see is 20 log of 10 of omega, log of omega on base 10. So, what we note is that as omega increases, the value of decibels increase, and it is a straight line on a log axis. So, the curve is something like this. The next thing we have to figure out is what is the point of intersection for the high and the low frequency asymptotes. So, at the point of intersection, the value of high frequency asymptote is same as value of low frequency asymptote, and that will happen when omega equals z. So, the corresponding position on the log axis is log of z or z. The next thing we want to know is what is the slope of this curve. So, we find out the slope, let us say dB1 equals 20 log of omega 1, dB2 is 20, and suppose I increase my angular frequency by a factor of 10, then it is 20 log of 10 omega 1. So, this is equal to 20 log of omega 1 plus 20, which means that for an increase in frequency by a factor of 10, dB goes up by 20. I increased the angular frequency by 10x, dB went up by 20, which means that the slope of this line is 20 decibels per decade actually. Yeah, actually I am going to write it at a different location. So, this slope is 20 dB per decade. Decibels per decade. And finally, we would like to see the actual response curve. So, the purple line is the asymptotic response, this is the low frequency asymptote, this is the high frequency asymptote, and the actual curve, actual response is if we plot this actual equation. So, we see that for any value of omega z plus j omega, its absolute magnitude is going to be higher, right. So, when I plot this, that is assuming z is real. So, when I plot it, this is my actual response. So, for a simple 0, actual response is always higher than asymptotic response for a system whose h of s is a simple 0 and z is real, and z is real. So, what we have seen is two Bode plots. In last class, we developed the Bode plot for a simple pole. The low frequency response was a straight line, horizontal line, and the high frequency was a negatively sloped line, slope was negative 20 decibels per decade. For a simple 0, the magnitude plot kind of looks like its mirror image. The high frequency response is a positively sloped line, low frequency response is a horizontal line which has 0 slope. So, these are the magnitude plots for a simple 0 and a simple pole. The next thing we are going to do is we will develop their phase plots. We will develop their phase plots. Bode plots for phase. So, the first thing we will do is for a simple 0 or for a, we will start with for a simple pole. So, h of s for a simple pole the transfer function is 1 over p plus s. Now, in the phase plot we do not take log and 20, all we have to do is compute the phase under two conditions, when omega is going to 0 and when omega is going to infinity. So, this thing is equal to, so first thing is we have to do is that we do all this discussion on both plots when s equals j omega. So, for s equals j omega, h of omega equals 1 by p plus j omega, and this can take two asymptotic values when omega approaches 0, then h of omega equals 1 over p, and when omega approaches infinity, then h of omega becomes, actually this should not be equal, this is an approaching value. So, this approaches 1 over p, in this case it h of omega approaches 1 over j omega, or it becomes j over omega minus j over omega. Now, here we make an assumption that if p is real and positive, if p is real and positive, then when omega approaches 0, we know that h of omega approaches 1 over p, which means phase of h, it approaches 0 radians, it approaches 0 radians. Why? Because the phase is imaginary component divided by the real component. The real component is positive, the imaginary component is 0. So, in the numerator I have 0, in the denominator I have a positive number, and in this case phase is 0 radians. When omega approaches infinity, h of omega approaches minus j over omega. So, what is this? This number is basically pure imaginary and it is negative, right. So, which means that phase of h is approaching tan inverse of negative omega divided by 0. So, this is equal to minus pi over 2, minus pi over 2. So, but remember this is true only if p is real and positive. If p is complex, then these things could change. Okay. We did not have this condition in context of the magnitude plots, but in context of phase plots, that value of p, whether it is real or imaginary and whether it is positive or negative, it has a role. So, now with this understanding, so when we develop a phase plot for a simple 0 or a simple pole, it will look like this. So, on the x axis I am going to plot log of omega, and once again it will have two asymptotes, low frequency and high frequency asymptote, and here on the y axis I am going to plot phase in radians So, the low frequency asymptote has a constant value 0 radians. So, this is my low frequency asymptote. So, this is 0 and the high frequency asymptote has a value of negative pi over 2 radians. So, that is my high frequency asymptote. And this is low frequency. The crossover point for these two will occur when 1 over p equals 1 over omega. So, this is here log of p. Okay. And if you have to plot the actual phase, then you have to plot the phase of this function, not the asymptotic function. So, in this case the plot will be tan inverse of omega divided by p, negative of that, because there is a j in the denominator. Okay. So, if that is the case and if you do that plot, then the actual phase plot will look something like this. So, this is the actual phase plot. And the green line is the asymptotic plot. Next, we will do the phase plot for a simple 0. So, earlier we had done a phase plot for a simple pole. Now, we are going to do a phase plot for a simple 0. So, in this case h of s is z plus s, it is a simple 0. And when we are doing Bode plots, s equals j omega. So, h of omega equals z plus j omega. Now, h of omega equals z plus j of j omega, in an asymptotic sense it can have two values or two functions. So, when omega approaches 0, h of omega approaches z and phase of h approaches 0 radians, because omega is tending to 0. So, it has only real component, imaginary by y. So, this is for the case. So, this is when z is real and positive. So, this is the condition. When z is real and then positive, then we can make this conclusion. When omega approaches a very large number, infinity, then h of omega approaches j omega and phase of h, omega is positive number, this approaches pi over 2 radians. Okay. So, in this case, when I do a plot, for phase, then this is my phase in radians. The low frequency asymptote is a horizontal line and the high frequency asymptote is also a horizontal line. So, that is my high frequency asymptote, this is my low frequency asymptote. And my 0 is here, and the actual response, if I have to plot, I have to plot the phase of this function assuming z is positive. So, when that is the case and if I plot it, the actual response will look something like this. So, this is the crossover point. So, that is the phase plot for a simple 0. So, what we have discussed till so far is how to construct Bode plots for simple zeros and simple poles, but real transfer functions may not necessarily be a simple 0 or a simple plot. In general, it can be represented as a multiple of zeros divided by a function which has several poles. So, now based on the discussions over last 2 lectures, we have learned how to construct phase and magnitude Bode plots for simple zeros and simple poles. So, what we will do next, which is in the next week, will be how to construct phase plots for real functions which are combinations of these zeros and poles. So, that concludes the discussion for this week, and please check your assignments, and I hope you do good in your assignments, and I look forward to seeing you next week on Monday. Thank you and have a nice weekend. Bye.